Well, he's got the way that it's constituted now. All right, ladies and gentlemen, good morning. I know this may sound like I know this may sound repeaty for you guys, but people who are watching it didn't hear that part. So, our plan for today is to take care of getting ready for your test, which is scheduled on you guys Wednesday, so tomorrow, first part of the block. As far as the test goes, first, it is not a double-length test just because we're taking out a block day. It's a regular size test. I think yesterday I put it to the copy center. I think it's 25 questions. No. I don't want to grade. I don't want to grade something that's 25 pages long.
Well, it's gonna be one question that you say.
I think points-wise, it was like 34 or something like that. So it's a little kind of a bigger test. I mean, it is like 2.5 weeks worth of stuff. So as far as topics go, this unit started back on April 16th. And we introduced the ideas of what energy was generally, and that we went over a couple of different types of energy, but then we shifted our focus to mechanical energy. And so in the mechanical energy section, we introduced kinetic energy, gravitational potential, elastic potential. Then we started talking about work, what work was. That's when you did your lab for your lab report with the pendulum and the ball going down the hill, okay? Then we also introduced the idea of conservative force versus non-conservative force. What happens to things when conservative forces are acting on them? What happens to things when non-conservative forces are acting on them? May 22nd. Then, last week we got into the idea of the thermal energy. We said that thermal energy more dealt with the motion of the particles, the atoms or molecules that make up that substance. We talked about the difference between temperature and thermal energy. We introduced the term heat. Then we talked about calorimetry and how we measure the amount of heat that is lost or gained by an object. And then over the past couple of days, we talked about energy transfer and how that energy gets from one place to another. Okay? So, as far as today is concerned, if you guys have questions, I will be glad to answer them. And I'll try to maybe repeat the question so when you're watching it again, you understand what the question was. Kirsten, start us off.
Okay. For the one that was describe convection, convention, radiation.
Okay. Okay. So the question was describing convection, conduction, and radiation, and then apply it to certain situations. Okay. So we talked about that there are certain requirements for certain types of heat transfer. Okay. First, in order for conduction to occur, we said what is required? There has to be touching. There has to be contact between the particles. Okay. If we go back to our analogy that we used in class, the idea of the note passing from one side of the room to the other, you guys are the particles that make up that substance. Okay. Conduction is the idea that one of you passes it to the next, passes it to the next, passes it to the next. Okay. You have to be close enough that you can actually get the note from one person to the next person. That's the touching aspect of it. Okay? Convection, we said, was when particles of a fluid move around. So first, if it says particles of a fluid, that excludes what state of matter? Solid. Because our example in class of the convection was somebody actually takes the note and walks it over to the other side of the room. So there has to be some movement of the substance. In a solid, you guys can't move from your position. You can twist and turn and wiggle, but you can't physically move. That's one of the characteristics of a solid. So that's what we talked about as far as particles of a fluid. And then with radiation, we said it was just the energy passing from one side of the room to the other. As far as the note example went, that was like if we take the note and we just throw it across the room. Okay? Does that make sense as far as describing it? Okay? So as far as what you're looking for, first, conduction. Is there some kind of contact, right? If there's no contact, there can't be any conduction. Is there conduction through a vacuum? What's in a vacuum? Nothing, right? So if there's nothing there, there's no matter there, Not a vacuum cleaner, like a vacuum, not, sorry.
Vacuum chamber.
Like the absence of anything, the absence of matter. No, black hole is lots of matter. Once you get out of our atmosphere. Okay.
It's like imagine a tube and you circulate air on it.
Is that? I'm sorry. Is that better? Okay. So if we have something that is a vacuum, right? There's the absence of matter. Will conduction occur in that space? Because you need to have touching. Can convection occur in that space?
No,
Because you need to have something to move around in convection, right?
radiation.
Radiation can occur because we don't need matter to throw the note from one side to the other side. As far as convection goes, we said the one requirement for convection is what has to happen to those particles that are inside of that substance or make up that substance. They have to what? They have to move. So you have to see some kind of movement within that substance. Okay? When you put, if you ever see it, like if you have something like really hot coffee, if somebody puts cream in it, you can see the cream moving around as it mixes together. That's convection, because those particles are moving, taking the heat transfer different places and that kind of stuff. Does that make sense? And then for radiation, there has to be some way for the energy to get from there to there, but there doesn't necessarily have to be anything in the way. Just because radiation can occur in the absence of matter doesn't mean that it won't occur if there is matter. Okay? Light and heat from the sun. There's nothing between the sun and the edge of our atmosphere, so radiation occurs during that space. But just because it gets to the edge of the atmosphere doesn't mean the radiation stops. That energy still transfers through the atmosphere. So a lot of kinds of radiation can go through matter, but they don't necessarily have to. Does that make sense? All right, next. Anthony, go ahead.
What is elastic?
Okay, what is elastic potential energy? We said elastic potential energy derives from, Chris, I saw you just make hand motion. It derives from what? Either stretching, or we could go the other way, compressing, right? Because if we stretch something out, right, this rubber, or what? Piece of gum is kind of an okay example, although it's, because with a piece of gum, if you stretch it out, we want it to be something that will try and do what when we stretch it out, or go back to the way that it was. And when it goes back to the way that it was, we can use that to move or change other things. Okay? Like, if the string on a bow and arrow, if you stretch that string out, it wants to go back to the way that it was. As it's going back to the way that it was, we can use it to push the arrow.
Okay, would it use to break it?
Okay. Now, there is a limit to how far we can stretch certain things, and that more depends on that material, how much elastic potential energy it can give, right? This rubber band can give a certain amount of elastic potential energy, but if we have something like a big, thick bungee cord or something like that, it can give a different amount of elastic potential energy based on what it's made out of and what it is. Okay? So, it does, when you calculate the amount of elastic potential energy, there are things in the formula to take into account those factors, what it's made of, how far you stretch it, but you don't need to know how to calculate elastic potential energy. Just tell me about it. Okay? Okay, go ahead.
What are like all the equations that we know?
All the equations you need to know. There are 3 equations that will show up on the test. 1, they will be on the test. And you need to know how to use them, but they will show up on the test. Okay? So, kinetic energy will be on the test. Okay. Gravitational potential energy will be on the test. Okay. The G is 10, the acceleration of gravity. So, we'll go 9. I mean, you have the number over on there. I mean,
So you want us to use 9.8?
What does Y stand for? What is Y again? Height. It's a height. This is the reference point.
Alright, so,
What's the
these,
when you know potential elastic?
so, as far as the formulas that will show up on the test, the first one is the kinetic energy, 1/2 mv squared. M stands for mass, V stands for, we said, really is speed, but you could throw velocity in there, because even if you have a negative velocity, what are you doing to the velocity in that formula anyway? You're squaring it, so it comes out to be a positive number. Okay? Next, gravitational potential energy, MGH. Yes, on the sign up here it says MGY, but H just stands for height, right? In physics class, we talked about a couple of different dimensions and axes and stuff like that. So I changed it to Y for, change it to Y for physics class just to show that it's a change on the Y axis, okay? Then the last formula that will show up is the Q is equal to M times C times delta T equation, okay? So we said that the Q is equal to M times C times delta T equation. Q stands for the amount of thermal energy that is transferred in a situation, which we said could also be the heat that is transferred in a situation. Remember, we said those are synonymous terms. Okay? M stands for the mass of the object. C stands for the specific heat value. That's a constant known value that I will give to you on the test if you need it. If I don't give it to you, that means you're probably solving for it. Okay? You don't need to memorize any specific heat values. Okay? And then delta T, the change in temperature. When we calculate the change in temperature of something or the change in anything, how do we calculate the change in anything? Final minus initial. That means that if your final temperature is lower than your initial temperature, what delta T is going to come out as? A negative number, because what happened to the temperature? It went down. Okay? That's okay. And that means if the temperature goes down, what probably happened, Nick? Did it gain energy or lose energy? Probably lost energy. And that means that the Q value is probably going to be what as well?
Energy lost.
Energy lost, so what sign should Q have in that equation? It should be negative as well. Okay? Does that make sense?
Like the one you gave us on our
Yep, the one you gave on your quiz. Yep. Or the lab that we did with heated method. Yep. Alright. Those are the three formulas. Nick, those are the three formulas that show up in this.
So Q is heat transfer.
Q is heat transfer. Yes. Allison, go ahead.
Okay, I have two.
Okay.
One of them is I really don't understand specific.
Okay. So, really don't understand specific heat. Specific heat is a property of the material that tells you how easy or hard it is to change the temperature of that material. Okay? Things that have high specific heat values tend to maintain their current temperature better than other things.
Oh, so it's harder to change the temperature.
Right. Maybe think of it kind of like inertia if you want to, right? Specific heat is like the inertia of temperature. High specific heat values mean that they will maintain their current temperature. It takes a lot to make them heat up. Okay?
It's like inertia.
That was hot. So
High specific heat, right? Yep. Then low specific heat values are easy to change their temperature. It doesn't take very much energy at all to make them heat up, or it doesn't take them losing much energy to cool down. Okay? Does that make sense?
Yeah, and then on the notes it says which part of the pie stays hot for longer.
Okay.
It would be inside.
Generally, the inside of the pie stays hotter than longer because that means it would have a, how would its specific heat value? It would be higher specific heat value. Because the crust of the pie has already cooled down 5 minutes after you take it out of the oven. But the inside of the pie still stays warm, meaning that it's harder to change its temperature, so it has a higher specific heat value. Okay?
And then also I don't understand the
You realize this is your third question. I just want you to know. You told me you had two questions.
this is my second.
The pie.
Oh yeah. Well that was like if A branched off.
Gotcha.
Okay. The next one.
Let's go 2A then. Okay, go. Yeah. 2A.
Describe the conversions of energy from one form to another when an object is only conservative force.
Okay. Conversion of energy from one form to another when only conservative forces are acting on it. So, beautiful. Thanks. Thank you. All right. So, got your hand, right? And then there's the ball in your hands. Okay? There. Just to make it
Taking a blue ball. A blue ball.
Purple.
Yeah.
Purple, purple.
So green. All right. So, Allison, first, conservative force, non-conservative force. Okay? We said that there are two kinds of conservative forces out there. Do you remember what the two of them are? Gravity is one, and then the other one is like elasticy, springy forces. And we said that what makes them important, okay? So conservative forces
The ball is on your
I'll
head.
go back into the reason right
Yeah.
now. It looks like a yarmulke.
Wait, no, you have to. No,
Too bad we don't have video of this. Only you guys, and you go back and watch it, will get to enjoy that. So, two types of conservative forces. Gravity force and then elasticy, rubber bandy, blah, blah, blah. Okay? But the important thing here is that when there are only conservative forces acting on the object, what do we know is true? Mechanical energy is conserved, right? Which, we said, is just a fancy way of saying mechanical energy is going to do what? Stay the same. Okay? So,
there's gravity elastic.
when there are only gravity or elastic, those are two separate kinds of forces. Okay? So, Allison, going back to our question, describe the energy conversions when there are only conservative forces. Okay? So, yes, when you're throwing the ball upward in the air, okay, I'm going to throw this ball up into the air. When I'm actually throwing it, when my hand is moving, is that a conservative force acting on the ball? Does my hand fall into one of these two categories? No, it doesn't. So while I'm throwing it, that's not a conservative force. That's work. And I'm giving the ball more energy because of what I'm doing to it. Okay? Now, the very moment that it leaves your hand, okay? Let's forget about air resistance and friction and all those things. From the moment it leaves my hand, what is the only force that's acting on it?
Your hand. Oh,
For the
gravity.
moment it
Gravity.
leaves my hand. It's got to be gravity. Yes, the ball is still going upward, but is my hand actually acting on it anymore?
Nine.
Why does the ball continue to go upward after I
Because
throw
of
it?
inertia.
Because of its inertia, right? But from the moment it leaves my hand, now gravity is affecting it. Okay? Let's say I make my measurements, whatever, and I say from this point where it left my hand, I'm going to call that like the bottom of my motion. Height equals 0. Okay? So how much potential gravitational energy will it have at that point in time? 0. Because if I'm going to call this height 0, if gravitational potential energy depends on height, and I'm at the 0 height, I don't have any gravitational potential energy. But what's happening to the ball at that moment? It's moving. So it has what kind of energy here?
Kinetic.
It has kinetic, but it doesn't have potential.
9.
Okay. On the way up, what's happening to the ball as I throw it into the air?
Kinetic energy is decreasing.
Let's talk
potential
about
is
its
increasing.
speed first, right? It's doing what?
Slowing
It's
down.
slowing down as it's getting what? As it's getting higher. So from an energy standpoint, the fact that it's slowing down means what's happening to its kinetic energy? Less kinetic energy, but because it's getting higher, its gravitational potential energy is increasing. Now, here's the important part, right? If there are only conservative forces acting on it, like if we forget about air resistance and friction and those kind of things, mechanical energy is conserved. Meaning that if I threw it down here at the bottom, in a way that gave it 100 joules of kinetic energy. And we talked about the idea that there was 0 gravitational potential energy. When it gets up to the top, what do we know has to happen up at the top? It has to stop. So for that instant up at the top, what is its kinetic energy? 0. But if there were only conservative forces and mechanical energy was conserved, if its kinetic energy went down by 100 joules, if it started with 100, now it has 0, what has to have happened to that potential gravitational energy? It has to have gone up.
Is that because you're doing it without right?
Right. If there's only conservative forces, only gravity or springy forces, right? In order for mechanical energy to be conserved, mechanical energy, remember, is the combination of this, and elastic potential, but nothing's being stretched or compressed in this problem, so we won't worry about elastic potential. If kinetic energy goes down by 100 joules, gravitational potential energy better go up by 100 joules to keep the total amount of energy equal to what? 100.
Is it a direct relationship between the two?
It's not exactly a direct relationship, but they do. Those are more inverse. Okay?
Oh, yeah.
Here, let's do this. Let's say this is 2 meters. I threw it 2 meters into the air. This is 1 meter.
Will they both be 50?
They'd both be 50 at this point. How do I know that potential gravitational energy has to be 50? Because it depends on what? Height. If I throw it 2 meters and it gets 100 joules of potential energy, at 1 meter, how many joules of potential energy is it going to have? 50. Okay? But if it's got 50 joules of potential energy, gravitational, how many joules of kinetic energy does it have to have? 50. Because if there's only conservative forces, mechanical energy has to be conserved. So the total always has to add up to what? 100. If I started with 100 joules. Wolf, go ahead.
So what if in this graphic we let it all drop below 0?
Okay. Now what if I let it drop below height 0? Okay. So if I let it eventually come down here, right? It started with, if we called that original height 0, it started with 0 gravitational potential energy. Okay? And it got 100, or it started with 100 kinetic energy. But, well, if mechanical energy has to be conserved, right, that means the total amount always has to be what? It's got to be 100. Okay? Let's say I go down to a spot that is 1 meter below where I threw it from. How much gravitational potential energy would it have at that spot? Negative 50. Does that make sense? We'll get that.
50 potential energy.
So, say again.
Negative 50 potential energy.
Right, because it's below where I started. Okay? And it's 1 meter below where I started. 1 meter above where I started, it had 50, but 1 meter below.
Yeah.
Now, Wolf, if that's the case, what does the total always have to add up to? 100. So how many joules of kinetic energy would I have to have at that point?
That makes
Because the acceleration
Now.
of gravity.
Let's think about that. Let's think about it, what it means, right? If it's going 100 joules right when it leaves my hand, or 100 joules of kinetic energy here, 150 joules of kinetic energy here, how fast is it going at this point versus this point? It has to be going faster, right? Yeah, absolutely. We said that gravity works in a way that if I catch it right where I threw it, how fast is it going when I caught it versus when I threw it? Exactly the same speed, right? But if I let it go past my hand, what does gravity keep doing to it? Faster, 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 faster until it hits the ground, right? So once it gets below my hand, it's going faster than I threw it. And that's why, how much kinetic energy will it have? More than I threw it with. Is that good, Wolf?
Yeah.
But Allison, getting back to relating it to your original question, if gravity is still the only force acting on it, what does the total always have to be? Got to be 100 because of the idea that mechanical energy is conserved. Okay? And that's what that question is asking you for. Okay. Lauren, go ahead.
So isn't there air resistance in this problem?
Right. So in this problem, in the real world, mechanical energy wouldn't be conserved. Okay? So let's do this.
Is there any situation in real life where it would be conserved?
Not here. Well, I suppose that's.
I mean, besides like outer space, so it's like
You have to get rid of friction and air resistance, which is pretty hard for us to do. Okay. So now, Lauren, let's go with the idea of a non-conservative force. Okay. If conservative forces are gravity and elastic, non-conservative forces are everything else. Okay? Friction, air resistance, me throwing, you pulling, you pushing, whatever it is. Okay? So now, Lauren, if we have non-conservative forces, mechanical energy is not conserved. So on the way up here, if I throw it with 100 joules of kinetic energy, friction, air resistance are moving against it that time while it's going up. Okay? So will it get to 100 joules of gravitational potential energy? Will it still end up with 0 joules of kinetic energy? Yeah, because what happens up at the top? It stops, right? But now, instead of this being 100, depending on, how much air resistance or friction we have, right, it might only be 98. Okay? Then, if it falls back down, right, I've thrown it to this point, it's got up to 98 or whatever, okay? As it comes back down, right, when it gets back to my hand, does it still have 0 gravitational potential energy? Yeah, because that depends on height. Will it have 100 joules of kinetic energy, what I threw it with? No. Will it have 98 joules of kinetic energy?
No.
Because it lost energy on the way up, right? But it will also lose energy on the way down. So it might only end up with like 96. Sorry, this must be a 6. I have an eraser when I use it. It might only end up with 96 joules of kinetic energy when the time it gets back to my hand. Because there are non-conservative forces acting on it all the time. Okay? Caroline, go ahead.
When you're at the ball, how can the potential gravitational energy be 0 if it's like, and you're talking about it's going under, like is it still a ball with gravity?
Now, Caroline, we said that gravitational potential energy, or the height of gravitational potential energy, depends on where you call the 0 point, right? If we have a ball that's sitting on the ground in this room, right?
Yeah.
Most of us would say, oh, that can't do any damage, it can't hurt me,
Yeah.
right? But what about somebody down at the bottom of the steps? Might hurt them, right? So the height in the MGH equation, okay, with that being, the height of the object, really depends on where you measure it from, okay? I just decided, you know what? Because this is where I threw it from, and this is where my problem started, I'm going to call that my 0 height. I'm going to call that my starting point. It's all relative about where you measure it from. But the thing you find out, Caroline, regardless of where you measure it from, if you look at the changes in potential energy going from here to here, regardless of where you measure it, you get the same answer. How much it changes or how much it goes up by the object raising into the air.
Okay, and then also if like the ball was sitting like in the middle of the desk, would it still have gravitational potential energy, just less?
Once again, it depends on where you
Okay,
measure it from. If it was floor, yeah, then it would still have gravitational potential energy, but no kinetic energy.
Okay, and same with if you're holding it, like it still has gravity.
As long as I'm holding it where? it would have the same amount of gravitational potential energy as long as I was holding it how high?
Oh,
The same
Oh,
height,
it is.
right? Moving it from here to here doesn't do anything to its gravitational potential energy. Moving it sideways doesn't change that at all. Oh, good.
So, what about like right before you catch it? Would it have potential for gravity?
Yeah, I suppose it depends on where, like, you know, where you set your 0 point, right? If it's right before I catch it, we can say, you know what, I'm right at that reference point, so we could say that that would be 0. That gets into like how you're measuring. Anthony, go ahead. Nope, it's gonna be a non-conservative force. Here's good.
So with the non-conservative forces, how you went from 98 joules to 96?
Yep.
Where's the rest of it?
So, where does the rest of it go? We talked about that a lot of non-conservative forces, especially like friction and air resistance, what happens to those objects as they are experiencing friction or air resistance? They get what? They get hotter. So that 4 joules that we lost from the time I threw it when it was 100 kinetic energy, now 96, that means what had to have happened in this room? It got hotter. How much hotter? Not necessarily temperature-wise, but energy-wise. 4 joules worth of heat energy have been created. Because in the end, the total amount of energy has to be equal to what? Has to be conserved. Does that make sense?
Yeah. So like it turned into thermal.
Yep, turned into thermal energy. So if we measured the temperature of the air as it was going through, we'd see that there should be an increase in that air temperature. Okay. Christian, go ahead.
I understand why it changes like from 196, but why does it change? Like, why is it 98?
On the way up, right? That's what air resistance has reduced it from 100 to 98. And then on the way back down, air resistance reduces it from 98 down to 96. Okay? Here's good.
For the law of conservation of mechanical energy, is that basically just like they'll always have like in this case 100 joules?
If what is the case?
If
If there are only conservative forces acting on it. That's the real key. Okay? That's the law of conservation of mechanical energy. If there are conservative forces acting on that object, it will maintain the same amount of mechanical energy, but only if there are conservative forces acting on it, and only conservative forces. Okay? Is that good? Sam, go ahead.
On the test, if there's like a question of this, will you be like, there are conservative forces acting,
Yeah.
or there are not
So,
conservative forces?
if I tell you what are things you're going to look at to tell you whether it's only conservative forces or non-conservative forces. Right? The one thing that generally we look for is this. If there is no air resistance, or if air resistance is neglected, okay, that tells you that something is flying through the air, what would be the only force acting on it?
So
Gravity.
we consider it.
Right. Okay. So Sam, that's what those are kind of the key things you're looking for. If the problem says, if gravity is the only force acting on this object, or if there is no air resistance, or if air resistance can be neglected, right? Those are all things, okay, conservative. Now, on the quiz, okay, the very first quiz I gave you in this section on mechanical energy, it said, there were 2 questions on the back, okay? One question said, if an object is thrown in the absence of air resistance, it was that same problem. It said, I gave it 100 joules of kinetic energy, how much potential energy does it end up with? Okay? The second problem said, if this experiment took place in a physics classroom on Earth.
Right.
In a physics classroom on Earth, what can't I get rid of?
Air
Air resistance. So am I going to end up with 100 joules of kinetic energy when it gets back to my hand? No. Does that make sense? So those are the keywords you're kind of looking for there. Okay. Anything good?
I have a question about heat.
Yeah.
If like an object has too much heat, will it like burst into flames?
It could be, yeah. If there's now, flames is a chemical reaction where is there some kind of a chemical reaction between that really hot object and something around it? Flames is a combustion reaction, so it needs to have fuel and oxygen. Okay, so if those conditions are met, yeah, it could. But if not, it'll just get like really, really hot. Okay. Chris, go ahead.
What's the operation of a calorimeter?
Operation of a calorimeter.
Yeah.
So, hints. This is where we go and look at critical thinking of what we've done in class. Okay? this kind of problem showed up where? This showed up where? There was kind of a problem where it showed up on the quiz, but what was this the gist of? Your lab report was basically this, right? Okay? And that was one lab that we did in class. Okay? The pendulum one. Yeah, the one you were lab report on. This is pretty much what your lab report was about. Okay? Now, the second lab that we did was the calorimeter lab. Okay? So, we got this insulator, right? And we said it was important that it was an insulator because we were focusing on what was going on inside, right? There's water inside of it, and then there was that hot metal sinker that we put inside, okay? What happened when we put the hot metal sinker into the cold water? It lost energy to the water, and the water what? Gained energy. We know that if we measured the mass of the water, its specific heat, and its temperature change, we could figure out how much energy the water gained. Okay? But the big assumption that we made was this hot metal sinker, if the water gained energy, where did it get it from? The metal sinker. So, we could do the same thing for the metal sinker, but what has to be true about these Q values? They have to be equal, but one's going to be positive and the other one's going to be negative, right? This is the second lab that you did, right? Any guess what kind of a problem might show up on the test?
That kind of problem.
This kind of problem, right? So the big assumption, the idea of the calorimeter being that inside there's going to be some energy transfer. The one substance is going to gain energy, the other substance is going to lose energy. How much? Exactly the same amount. So if we can calculate the Q value for either one of those substances, we automatically know the Q value for the other one, just one's positive and one's negative. Okay? Rhea, go ahead.
So, again, that's like we take the same amount of thermal energy.
Yes.
Don't lose or gain the same amount.
Right. Because temperature also depends on specific heat, right? Remember we talked earlier that specific heat is how easy or hard it is to change the temperature. How much energy do you have to put into it to change the temperature? Does that make sense?
The water gain as much as the metal lost and then the higher.
It gained the same amount of energy, the water gained the same amount of energy as the metal, but its temperature change wasn't the same because they have different specific heat values.
Let's say somebody in your class